Hello, welcome to 15.1 Aqueous Solutions and the Concept of pH. Be sure to answer the intro questions before continuing on. So some understanding key terms for success. Hydronium and hydroxide are very important ions that we'll be using quite a bit throughout the next couple sections, so make sure you're well aware of which one's which and what they're attracted to, as far as hydronium being acidic and hydroxide being basic. Those are very key parts that make things a lot easier if you keep those straight. So hydronium and hydroxide concentration. In water, there's a very, very low molarity with these. We see quite a bit low molarity, 10 to the negative 7th. However, it's equal. So you see that all of these are equal. Hydronium and hydroxide concentration in neutral water, where there's nothing else, are both equal. And you see these little brackets. These brackets are meant to be molarity. So you see, if you have the brackets, you don't need the capital M for molarity. That's going to be very commonplace over the next section. So what this means is that when these two are multiplied together, there's a little multiplication here, this is going to make a constant which is on your reference sheet, and you're going to get used to using it quite a bit. This will help us determine later on pH and pOH. Even though it's not really used, it can be used if you choose to. But that's not really going to be much of importance as pH is. So in looking at these, you use this term up here, the Kw, the product ionization constant of water, in order to determine one of your two ions. You get one of them, and then you need to determine your other. So in just looking at these small weird numbers, if they're equal, then your solution is neutral. If the hydronium is less than your hydroxide, it's basic. If your hydronium is more concentrated than the hydroxide, it's acidic. I never understood how to read these things till I got to college. I always just say that it points at the smaller one. So the idea is that this has less hydroxide than hydronium, and this one has less hydronium than hydroxide. Okay? And that's why it's basic, because there's less acid particles. And over here, it's more acidic because there's more acid particles than bases. Down here you can see water as a neutral compound. It donates one of its hydrogens to the other, and this is where we get hydronium and we get hydroxide. Be sure to tell that when you're looking at scientific notation, the lower exponent means smaller amount. So remember, 10 to the negative 8th is less than 10 to the negative 7th. So keep that in mind. Keep that in mind, that the bigger the negative exponent, the smaller amount. Now, one thing that's not mentioned too much in the book, but is one of our standards, is buffers. So a buffer is a mixture or solution that can resist changes in pH. The setup is really a weak acid with its salt. So I gave an example. This is acetic acid with its salt of like a sodium acetate, in which we have acetic acid and water being made. So the way this works is that if some acid's added, the acetate ions react with the added hydronium to make acetate molecules. So I show this over here. Get a little closer. This is a hydronium in the middle. So we really have very little of it when we start. However, if we add an acid to it, like HCl, a strong acid, and we put that in there, we see that some of the water does break down as there's less water molecules, but we still only have one hydronium here in the same. So we see that the HCl, which used to be these orange and light blue dots, now separate into individual chloride ions, which are scattered about, and some acetate ions, a little more prevalent than they were before, or a little less prevalent than they were before, because there was a lot more of them over here. I don't know, it's probably about 7 or 8. So you see that the acetate ions, there's less of those, and they're occupied by a little bit more of the HA, which would be the acetic acid. But the measurement of pH only comes from the amount of hydronium, and in both cases it's the same. Now buffers with bases reacts much the same way. If a base is added, the OH reacts with the hydronium to make water. Acetic acid molecules then ionize, making more hydronium to replace what's reacted. Super important in things like blood, CO2 we breathe in, as we learned about in the video. With the oceans, more CO2 means more acidification of the oceans, same with our blood. So many of our medicines are buffered so they don't disrupt things, like you'll see a lot of times they have HCl on them, in which that'll mean that they're buffered in order to not mess with our biological systems. So over here, a base is a mix of hydroxide and positive ions. So all of these are hydroxides. So when we add those to here, we see that we only have about one hydronium and then the scattered molecules. When we add the hydroxides, those will bond with the little light blue acid H+ particles, just the little light blue ones, to produce a lot of water. And of course, water doesn't change the pH any. So then it's leaving the rest of these little positive ions, the green dots. They have no bearing on pH at all. Now it does look like one of these disappeared, but a small change in hydronium is not that much of a difference due to the fact that we added so much hydroxide. The idea is that over here on this side we have 0 hydroxide, whoops, 0 hydroxide, and over here I'm not seeing any other hydroxides either, 0 hydroxide. So that means there's no overall change. Alright, so let's look on to some of the calculations. So looking at this, you're determining hydronium or hydroxide concentration, usually given starting off with a molarity. So big part is that an acid deals with hydronium, a base deals with hydroxide. Those are huge. We're only using strong acids and bases, so this rule will always apply to us. If you go into AP, you'll need to look at some other parts to it. But essentially, you follow the directions in which it's pretty straightforward to get this, and in some cases this is your only question. In other parts, there's much more to it. So let's look at some examples. So example of hydronium and hydroxide concentration if we're given a 0.01 molar solution of H2SO4. So the first thing you need to see, is this an acid or is it a base? I see that it starts with H, so I know it's an acid. And I also see that there is 2 hydrogens. So what I need to understand is that the molarity is going to be multiplied by 2 because there's 2 hydrogen ions that are going to break apart when this thing ionizes in solution. So that means that this is 0.02 molar for my hydronium concentration. So now that I have my hydronium concentration, I need to determine my hydroxide, and that's where I use the product constant of water, which is that hydronium times hydroxide concentration is equal to 1 times 10 to the negative 14th. It's technically molarity squared, but in the end you're going to end up with a molarity anyways. So I see my Kw is equal to, or my Kw over my hydronium concentration is equal to my hydroxide concentration, and yes, I'd like you to see you do all of this. This is good practice, and you'll only get better by doing. Take negative 14th divided by my 0.02, which is going to give me 5 times 10 to the negative 13th. And of course, because this is a brackets with the hydroxide, I don't need to put the M. That's why it's not terribly important to have that. Now try the next one, this one, on your own, and come back after pausing it and doing it and see how you did. Alright, welcome back. So first off, hopefully you answered the question that this is basic because there is a hydroxide present. So that means this molarity is going to relate to the hydroxides, and we see that there's two of them, in which when we're talking about this, the calcium hydroxide is an ionic salt, and when it goes into water, it's going to break into a calcium 2 plus ion and 2 hydroxide ions. So whatever we start with here, we're going to have twice as much hydroxide in the end. So that's why my molarity for hydroxide is going to be twice as my molarity for calcium hydroxide, so that's 2.0 times 10 to the negative fourth molarity. And again, now that I have that, it's going to be much more of the same, in which I'm going to have my Kw equal to the product of hydronium times hydroxide, in which when I rearrange that, I get my Kw over my hydroxide amount equals my hydronium. And so that's going to be equal to 1 times 10 to the negative 14th. You might recognize that's always going to go on top because you're going to divide by the other one that you find out in the problem. Negative fourth gives me 5 times 10 to the negative 11th. If you're not getting these exact answers, you're using your calculator wrong, and that's something you really need to be able to do at this point in the game. So let's look next at pH. So pH you've probably heard of from times in either middle school or maybe around your house. pH is a normal way to talk about acidity or alkalinity, which is the basic side, for any type of solution. And it's far simpler than looking at those scientific notation numbers and makes a lot more sense. So you still use your calculator, negative log of H3O plus, and that the POH is again just using the hydroxide concentration, but don't worry too much about that. So if the acid or base is strong, and remember being strong is the only ones we're going to talk about, that means its molarity is equal to the concentration times the representative ion given in the formula. And if we look at our dividing line of acids and bases, we see that acids, for the most part, are things we put in our body. Water, stomach acid, black tea, apple juice, battery acid, no. While other things we generally do not put in our bodies, with the exception of maybe an antacid. Oops, an antacid here. So if we're looking again at some other examples of stuff, most of the things that go in your body, most foods, if we have here, well, let's include blood, because blood is in our bodies, last time I checked. Most of our things are acidic, and most things are not acidic in our everyday life. Eggs, that also is incorporated. So a lot of everyday foods are acidic. There's a good reason for that. We're not going to go that far. Now, one of the other things talking about weak acids and bases. So right here we have a strong base and a weak base. We see that they're both the same concentration, but look at the amount of hydronium. Okay, far less in the strong base, less in the weak base, because less of it ionizes. Stronger base, stronger pH. Down here we have a strong acid and then a weak acid. Even though this one is 100 times more diluted, 100 times less concentrated, it actually is almost as concentrated of hydronium as this more concentrated weak acid. That's why its pHs are very similar. So again, strong and weak has to do with the chemicals. Concentrated or dilute has to do with the molarities. Okay, make sure you have that straight before moving on. So, determining pH and concentration from pH. So, most of it you've started off with already. And then once you get to your concentration, once you get here, then you just use your formula, which is also given on your reference sheet. Now if you're given the pH, you use what's called the anti-log. It looks like the 10 to the X button, and you finally get to use it if you've been misusing it for scientific notation from here on. So you finally get to use it, and there's a negative in there, and this will give you your hydroxide concentration. The hydronium concentration. If you need the hydroxide concentration, stuff from the previous slide will talk to you about how to do that, just as you've already done that so far. Alright, so first thing, acidic or basic, looking at HNO3. Hopefully you'll recognize that this is acidic. So there's one hydrogen, so that means my hydronium concentration is going to be equal to my molarity. Pretty easy now. So now I just need to take my negative log of my hydronium is equal to my pH, which means negative log of my 3.72 times 10 to the negative fifth is going to be equal to 4.43. Now some of you might go, sig figs, what are the sig figs on this? Significant figures with pH actually is a little more challenging in real practice than normal. A few decimal places for pHs, let's stick with that, okay? Don't be too overly cautious or worried about sig figs in this section. So again, acidic or basic? Well, I first need to see SrOH2. OH means it's basic. So this is going to tell me information about hydroxide, and I see there's two hydroxides, so this is going to be times 2. So 4.0 times 10 to the negative second is my hydroxide concentration. But pH deals with hydronium. So I'm going to need to find my hydronium concentration. Again, my Kw is that product of those. So Kw divided by my hydroxide in this case equals my hydronium. So that would be my 1 times 10 to the negative 14th divided by my 4.0 times 10 to the negative 2, which gives me 5 times 10 to the negative 6th. Oh, I'm sorry, I was looking at the wrong one. That gives me, let's erase this. That gives me 2.5 times 10 to the negative 13. And so then the negative log of that value, 2.5 times 10 to the negative 13, is equal to my 12.6. Alright, so next we have, if we're given a pH, how much hydroxide and hydronium is there. So, given the pH, the anti-log of the pH is equal to the hydronium concentration. And again, you have that at your disposal. So 10 to the negative 1.5 is going to be equal to 3.17 times 10 to the negative 2 for my hydronium. Now we just use that product of water, Kw, to find the hydroxide. Kw divided by the hydronium. So you see we're using a lot of little bits over and over again in various situations. One reason sig figs, I'm not going to be too stressed out on this, is that that product of water really only has like one sig fig, or often it only shows one sig fig. So for this we get 3.16 times 10 to the negative 13th for the hydroxide. So now it's your turn. Take a moment to pause and come back after you've done the next 3 problems. Alright, so welcome back. If you feel you got those right answers, then you probably don't need to continue on, but if not, here's the solutions for each of those. So pH 8.7, you might notice that this is slightly basic because it's above 7. Be aware of where you are on your pH scale. But again, pH only tells us about hydronium. So we'll have to take the anti-log of that, 10 to the negative 8.7, and that's going to give me my hydronium that we get here, 2 times 10 to the negative 9th. And to determine my hydroxide, I need to use my product of water again. Because that's the only way I can determine my other portion. To hydroxide, in which that will be 1 times 10 to the negative 14th. Probably have it memorized by now. To get the 2 times 10 to the negative 9th, that's going to be 5 times 10 to the negative 6th molarity. Alright, so next in line. So we have a pH of a base. That's why you know it's basic. So at 10.0, so again the pH is going to tell us only about the hydronium. So 10 to the negative pH tells us about hydronium. And so if that's true, 10 to the negative 10 is equal to 1 times 10 to the negative 10, and that's for the hydronium. So for the hydroxide, we need to use our Kw again. Super handy, of course. Really the only thing you can use to get my hydroxide. So that's going to be my 1 times 10 to the negative 14th all over my 1 times 10 to the negative 10, and this is where I get my 1 times 10 to the negative 4th as my hydroxide concentration. Now the molarity of my solution is a little different. Back a little bit ago I showed you that calcium hydroxide breaks up into 1 calcium ion and 2 hydroxide ions. So if that means my molarity for this is what it is, then that this is a 2 to 1 ratio of hydroxide to calcium hydroxide. So that's why I would take this molarity, divide it by 2, and this will give me the molarity of the calcium hydroxide solution, which would be very important because just from pH alone I can determine what that concentration is without having to do any other chemical tests. Now we have our last one, a molar solution of NaOH. Hopefully you recognize OH being basic, and I'm looking for the pH here. So what I need first is the hydronium concentration. I've got the hydroxide. The hydroxide concentration is that because I only have 1 OH here. So I can take my Kw, obviously divide it by my hydroxide, which gives me 1.35 times 10 to the negative 11th. That's my hydronium. So then I take the negative log of that value, Again, if you're using your calculator right, you'll get this fine. If not, you want to find out how to do that correctly to get your 10.87. Alright, so that's it for your turn. Be sure to answer the review questions, and I'll see you in class.